Hello everyone, I'm Xueyang Kang, and today I'm presenting our CVPR 2026 paper, Hierarchical Point-Patch Fusion with Adaptive Patch Codebook for 3D Shape Anomaly Detection. This is a joint work with collaborators from University of Melbourne, Tsinghua University, New South Wales City, and TU Delft. Our method targets the kinds of defects shown at the bottom: bogies, sinks, holes, which are local defects, planar shifts, angular misalignments, and surface defects. The last three are structural global defects. This is the whole picture diagram of our proposed method. On the left are 6 normal patches extracted from normal shape. On the top, their anomalous counterparts are presented. The similarity heat map between the different patch features shows strong diagonal almost everywhere, except the last row where the anomaly exists. That broken patch part feature highlighted in red is exactly the patch feature signal average. We turn patch level discrepancies into point level anomaly predictions, producing the localized detection you see on the right. The defects that matter most in the industrial inspection are often the ones existing methods cannot detect. Real manufacture produces planar shifts, angular misalignments, and large part displacements. Defects that span entire parts, not single points. The problem is that the current 3D detectors are built around local point feature, so they can only spot some small crack but miss a misaligned gear or planar offset entirely. We call this the defect gap, and we're trying to solve this problem. 3 families of methods are listed here. Reconstruction-based methods like R3D-AD become unstable on flat and concave regions, and they require a lot of negative augmentation. Key point and point-wise approaches such as PO3AD excel at small local defects but lose large structural displacements. Memory bank methods like ISMP store only point-level features and miss multi-scaled context. Our key idea is simple. First, cache. Second, compare. Third, fusion. First, we extract multi-scale patches from normal shapes at different scales and store them in lightweight position invariant codebook. Second, test the patches queries codebook through causing similarity independently on each scale. Third, retrieved patch per feature are fused into per point features through rotary positional embedding, cross-attention, and gated modulation. The right panel shows our small, compact, reusable codebook across different scales. The full pipeline runs in 4 stages. We start with a point cloud, a normal template during training, a test shape at inference. At stage A, we extract the translation invariant patch features by encoding patch relative to its old centroid. Stage B, we retrieve the most similar normal patches from the codebook. The codebook is pre-built during the training and query in inference. At stage C, our enhanced cross-attention will fuse patch feature into point feature. Stage D, we apply gated modulation driven by patch level discrepancies. The output is per point offsize, whose magnitude becomes anomaly score. The whole model can be formulated into 4 main expressions. Equation 1 defines our translation invariant patch feature. Equation 2 selects the optimal scale by argmax over some of the causing similarities between query retrieved patches. Equation 3 is gated modulation. Equation 4 combines 3 losses: direction, sign, and offset magnitudes. We reach state-of-art across 3 dataset benchmarks. Our self-made new industrial test set the gain is 40% at the point level for the planar and angular displacements, where existing methods essentially fail. The qualitative results show our anomaly point prediction against ground truth across various types of defects. Here are the 3 points to take with you. The code book is reusable and multi-scale. Second, the cross-tension compared with gated modulation will amplify the patch point mismatches of anomalies. And third, the same model handles everything from surface defects to structural part misalignments. Code paper and contact details are on the right. Thanks for your attention. Feel free to use and share our work.